foster circularity. And we should increase the use of refills in the market. And that is very important so that we can achieve a more sustainable society, a more sustainable consumption chain. So the first step, as we discussed yesterday, is that we have to communicate to consumers. We have to explain them why this option is more sustainable and why they should use refills. But because if you are going to move sustainability, we have to change consumers' behaviors. We have to engage them. But what I would like to discuss with you, in the market, at least in my country, when you are going to buy this pouch, it costs almost as much as the original bottle. But here you are buying a different value. Here you have a rigid packaging with functionality. You can open it and close it. You can take it in your trip with you in your necessaire when you need. And this one is just a refill pouch. So if we want to change consumer behaviors towards sustainability, we should not charge the same, not have the same price. We need to be strategic on how we position this product in order to change consumer behaviors. Again, I showed this example yesterday. We have to make it intentional. So this case is a very interesting case from Australia, where they tell consumer how to dispose of this empty packaging to make sure it's going to go through the recycling stream. So if we want to work on sustainability trends, we must be intentional. It's not only about the packaging material, it's about how we place this product in the market in such a way that it's going to fulfill the sustainability expected. It's going to guarantee a more sustainable consumption chain and a more sustainable society. Also here, another example, we have to make it intentional and easy for consumers to understand and to change their behaviors towards sustainability. Also, another very quickly example, we see in the market many recycled materials in different packaging products like consumer goods. And again, you can tell me but Luciana, using recycled material here costs more, it's more expensive. But consumers are not paying for it. Because what is the value to consumers? Delivering recycled materials is a value for the brands because it is the ESG agenda. It's their responsibility. If you want to offer consumers a more costly product because it's sustainable, you have to expand the benefit. And not only the packaging should be sustainable, but the product should be sustainable as well. So there is the purpose behind it. And you deliver a more sustainable product with a stronger purpose and also with recycled packaging material. So just to show you that we have to go beyond packaging in order to achieve and build new trends. Also another very interesting example, it's about open your innovation and really foster collective intelligence. I will explain you more about this. Also yesterday I showed you this picture. The household segment is trying to go circular. They are trying to find ways to sell refills to their original bottles. But each company is working on a different technology. They are spending a lot of money. They are spending a lot of time to have their own technology. So when we talk about collective intelligence, if they were working all together, and together they were developing one single technology to make sure they can have a refill product in the market, they would save money, they would save time. So that means if they collaborate, they can escalate changes. Especially if we consider that in the packaging industry, volume, scale of production is crucial. So if you want to have a solution just for your product, you may not meet the scale of volume production that would be cost effective. The same goes on with monomaterials that are recycle ready. In Japan, we saw some solutions like OPP materials, OPE materials, or paper materials. But at that point, only the coating industry was offering this solution. So how can you scale if you don't have the entire industry supporting you to scale this innovation? So we saw some examples in the market, but they were isolated cases. It's not that the industry was going through a new trend. And then finally at Interpack, like 2 months ago in Germany, what we saw going on is the entire industry fostering the new trend on monomaterials. And then we saw machinery producers offering solutions. We saw packaging producers offering some solutions. That means now we have the entire industry working on this collective intelligence, focusing on collaboration to foster new technologies and possibilities. And that goes on in our industry. This is a very interesting packaging, just to give you an example, that you can see in different countries. The same type of packaging, a pouch with a zipper, that can be found in Brazil or can be found, for example, in Japan. The same packaging. In Japan, they are brighter because Japan is like very colorful packaging that communicates with consumers. In Brazil, perhaps they are more cost-effective because our economy is not that strong. But what is the key point here? This technology is largely available in the industry. You can have it in small scales or in larger scales, and that's why different brands all over the globe can use this technology to grow. Another example. During the pandemic, we saw the restrictions of access to different packaging materials. Globally, companies weren't be able to export products. We saw a lack of packaging materials around the globe. So this kind of packaging, that is a standard glass bottle, they were available to brands, and with that, many creamy products they turned into serum, to liquid products, because this packaging was available. So as an industry, we have to make sure that we work with partners and we collaborate with other industry so that we have all that solution available to brands and consumers. Very quickly from retail, I think that we always have to understand that retail is changing the FMCG's market. But what I want to talk to you is that it's not about retail only anymore. It's about the supply chain strategy. So what is shifting in the market? So far, the market was driven by the supply, by the retail demand. And nowadays, the consumer's demand is the one driving the market. What does it mean to us? It means that every brand must be ready to reach consumers wherever they are. So either if it's online shopping, either if you go to a store, or sometimes the store comes to you and you have a store in your building, in your neighborhood. So nowadays, being ready to supply, to attend, to cope with the supply chain dynamics is very essential, and that's a huge global trend. So not about packaging itself, but how you are ready to fulfill the market and to fulfill very specific demands that could be one single product to one single consumers or a big retail shopping. So all kinds of retails now are there available. And imagine when the 5G, this new technology that will connect everything, when it becomes a reality globally, and anyone can just ask Amazon, hey, please, can I have another laundry soap? And then the system, the computer, is connecting with the supermarket to make sure they can deliver you one laundry soap. So the supply chain dynamic will change a lot how our market, the dynamics of our market. And then last one, my time is over already. Just I would like to point that we have to make packaging connected to as a smart packaging, as a solution to bring more information to consumers. So we are not really exploring this so far, but I believe with 5G that we have a better connection. We may grow a lot in smart packaging solutions that will enhance how consumers can reach your company, reach your product in order to have more information. So the alternatives are there. You have augmented reality, you have connections or traceability, all type of solutions that will engage consumers, that will bring a different experience to consumers, and that will offer consumer a connection with their brand. I want to share you a case on top of that. My son, some years ago, now he has grown up, he's taller than me, but when he was smaller, during the pandemic, he was cooking at home. So he wanted to prepare something sweet to eat, and he got this Kit Kat to prepare a new recipe. Imagine if in this packaging, we could find a QR code that he could read it and go to a website from Nestle and get the recipe from Nestle perspective. And then Nestle could offer, why don't you use other products like the chocolate powder from Nestle? Why don't you use another product from Nestle? So brands are missing the opportunity to build a real connection with consumers. So nowadays, what he did, he Googled himself a recipe, and then he found anyone that told him how to do this snack for him. But Nestle missed the opportunity to teach him how to prepare it. And that goes beyond packaging, because the packaging is just the platform to connect the brand and the consumer. So brands, when they understand they have to use packaging strategically, other segments of the company may be involved. The communication and the marketing segments are the one preparing this video, engaging some influencers that will be the one connected via packaging to talk to consumers. And imagine also when we have the metaverse growing. It's not growing at this moment, but it may come back and grow. And then, of course, we have packaging as a very strategic tool to connect consumers to these other digital worlds. So this is what I wanted to share with you today, that we have to explore packaging from an holistic approach. Not only looking at packaging itself, but the product and the market strategy. And of course, always enchanting consumers, innovating constantly, and delivering value to consumers. So, thank you very much.
Thank you. Thank you. Thank you very much to Mrs. Luciana Pellegrino, Senior Vice President for Marketing World Packaging Organization, or WPO. So once again, to give a big round of applause for your wonderful speech. Thank you so much. All right, ladies and gentlemen, and the next session is Q&A session, or we have discussion for this session. Anyone, if you want to ask about any question by our moderator, and he is the president of WPO, so everyone can ask any question to him. All right, ladies and gentlemen, may I turn the stage to Professor Pierre. Please give a big round of applause to welcome him. Thank you. Please welcome.
Thanks very much, everyone. Nice to be with you this afternoon. But it's more about the presentation that just happened. I'm sure there must be some questions that's on your mind regarding Luciana's presentation. Fantastic presentation, Luciana. Well done. That's great.
Thank you. Well, I'll be here if someone wants to talk. I'll be just here.
Right. Well, any questions? All right, Luciana will be there for anyone. Thank you very much. We will resume again at 2 o'clock. 2 o'clock.
Yes, yes.
At 2 o'clock. Yeah. All right, we're doing paperboard at 2 o'clock, and at 3 o'clock, plastics. Thank you.
2 o'clock, yes. Okay, okay. ค่ะโอเคนะคะเดี๋ยวเราจะกลับมาตรงนี้นะคะช่วงเวลาบ่าย2โมงนะคะกับในช่วงของท็อปิกถัดไปนะคะนั่นก็คือ material selection paper and board นั่นเองนะคะ so okay for this session no one has any question right alright we will come back right here again at 2 p.m. for the topic material selection paper and board by Professor Pierre Piana the President World Packaging Organization WPO once again at 2 o'clock. So I would like to welcome all of you if you are interested for the topic about material selection. The first session after this is paper and board, and after that is the material selection as well, but it's about plastics. Okay, anyone, if you want to know more about this, so you can come here and have a seat at 2 p.m. Okay, see you then later. Thank you very much. I hope to see you all as soon. Okay, make appointments with you all at 2 p.m. Thank you very much. your attention, please, ladies and gentlemen, everyone. So, as we are about to begin, for the topic for the next is about about the material selection, paper and board, and for the next is material selection, plastic. So I would like to invite you all, if you want to join us for the seminar right here for this session. So could you please have a seat? And for the seminar will begin as soon. Thank you very much, you all. All right, ladies and gentlemen, once again to remind you that we have made appointment with everyone, your honorable guests and our esteemed guests right here for joining us the seminar with the topic of material selection, paper and board, and plastic as well for 3 hours by our important speaker today. He is Professor Pierre. And of course, he is the president of WPO. Everyone can enjoy us for this special moment together and please have a seat. สวัสดีทุกท่านเลยนะคะสำหรับในช่วงนี้ค่ะสัมมนาในหัวข้อถัดไปของเรานะคะนั่นก็คือหัวข้อ Material Selection Paper and Board และพลาสติกนะคะเพราะฉะนั้นถ้าหากว่าท่านใดที่สนใจค่ะอยากจะเข้าร่วมการสัมมนาในวันนี้นะคะเพื่อฟังการบรรยายค่ะจาก The President ของ WPO นะคะประธานบริษัท WPO ค่ะหรือว่า World Packaging Organization นะคะสามารถที่จะแวะเข้ามานั่งกันตรงนี้แล้วก็ฟังค่ะกับหัวข้อดีๆนะคะนั่นก็คือ Material Selection นะคะการคัดเลือกค่ะนะคะวัสดุนะคะต่างๆนั่นเองประเภทกระดาษแล้วก็บอร์ดนะคะแล้วก็อีก1เซสชันของเรานะคะถัดมานั่นก็คือการเลือกค่ะนะคะวัสดุประเภทพลาสติกเรามาดูเคล็ดลับหรือว่า tactics นะคะไม่ว่าจะเป็นทางด้านของ material selection paper and board นะคะหรือว่าพลาสติกก็ตามถ้าใครที่อยากจะทราบวันนี้เดี๋ยวท่านประธานบริษัทนะคะของ WPO ค่ะจะได้มานะคะอธิบายแล้วก็ให้ข้อมูลอันเป็นประโยชน์ให้กับทุกท่านในงานนี้กันอย่างแน่นอนเลยค่ะเดี๋ยวอีกสักครู่นะคะก็ให้ทุกท่านเนี่ยพักกันก่อนได้นะคะแป๊บหนึ่งแล้วก็เดี๋ยวเราเนี่ยจะได้นำพาทุกท่านเข้าสู่ในช่วงของงานสัมมนาเล็กๆของเราตรงนี้ที่ Innovation Stage นะคะอยู่บริเวณทางเดินด้านหน้าค่ะของฮ98ถ้าเกิดว่ามองมาเนี่ยนะคะก็คือจะอยู่บริเวณหัวมุมเลยค่ะเดินมาตามทางเดินนะคะจะอยู่ตรงมุมนะคะด้านนอกของฮ98ค่ะทางที่จะเดินไปรถไฟฟ้า BTS นะคะเผื่อท่านใดที่อยากจะมานั่งฟังนะคะกับหัวข้อ Material Selection Paper and Board and Plastic Topics นะคะก็สามารถที่จะมารับฟังกันนะคะในหัวข้อการบรรยายในครั้งนี้ได้นะคะเรียนเชิญได้เลยนะคะ so ladies and gentlemen may I invite you or anyone if you are interested for the topics by our special guest today with the topic material selection, paper and board, and also the material selection, plastic as well. Okay, so for the two last presentation on these presentations that we proud to present to you right here, may I invite you all at the foyer hall 89. Okay, once again, the foyer, hall number 89, outside or the walkway. When you are working in the ProPack Asia events right here, so anyone can see that we are at the corner before you are going to the BTS station, and then. Okay, our mini stage over here that everyone can see for the green screen. Same like this. Okay, everyone can join us. Thank you so much. โอเคเชิญนะคะใครอยากจะรับฟังนะคะกับหัวข้อของเรานะคะเรียนเชิญมานั่งจับจองกันด้านหน้าได้เลยค่ะ Alright, everyone. Are you ready for our seminar for the next topics that is very interesting? Material selection, paper and board. All right, and for this session or these topics will present by our Professor Pierre Pierre, the President of World Packaging Organization (WPO). So without further ado, ladies and gentlemen, please welcome Professor Pierre. ขอเสียงปรบมือต้อนรับคุณปีแอร์ด้วยค่ะเรียนเชิญเลยนะคะ
Good afternoon, everyone. Nice to be back again. This is going to be more sort of a technical approach as opposed to what the presentations were earlier on, which is more marketing approach or graphics and images. So I'm going to deal with paper and paperboard, and then later on this afternoon we'll do plastics in packaging, which will include flexibles. At any stage, please stop and ask if there's anything you're not clear about or want to know more about or not sure about. They always say that the worst question is the one you don't ask. So no question is a silly question. We have to learn, both myself and all of you. All right, so let's start. We all know that, well, I'm sure we all know that paper comes from trees. And that we should conserve the number of trees that are in existence, but we should replenish them. So that's the good thing. They are replenishable, which is great. All right, let's have a look at just going through it for those who are not in the paper industry or want to know more about the paper industry. Certainly for those of you who are in the paper industry, this is not new for you. So we have the trees, we've got to find, ultimately debark them, we've got to chip them into little chips, called a chipper, and then we can put them through thermomechanical. So there's a lot of heat involved in paper. And I'm emphasizing that there's a lot of heat involved in paper because this is the area where the life cycle assessment or life cycle analysis becomes an issue. So I'm just mentioning that. We will touch on it later again, but there's a lot of questions being asked all the time regarding the LCA, life cycle assessment, between plastics and paper. So we'll touch on that so you get a better understanding and you can make the decision yourselves in your own companies. All right. Now, so that's from trees, but at the same time, right across the world, and this is what the good thing is about paper, there's massive amounts of paper being recycled, and that's really good. If one looks at the amount of plastics that's being recycled around the world, it is really bad, really bad. It's below 20%. Now that's a shocker. In this age, in this advanced technology age of ours, and we're only recycling something like anything between 16 and 20% globally on plastics. Paper is probably the best in every country's paper. Glass is up there as well. We did glass and we did metal yesterday, so I won't touch on that again today. But it's encouraging to see the amount that is recycled, and this is how we recycle. So it's a matter of the collection. That's where the problem lies in most of the countries, is that the collection points are not always there. The infrastructure is not available for you and I. Because we want to recycle, but where do I put it? Where do I take the can that you've just finished the water? Where do I place it to make sure that it's going to be recycled? And that's the challenge. Okay, so again, curbside collection. Again, we are, to some degree, we try and clean what we can. Now, this is a bit of an issue sometimes because if you have a pizza box, and you've got oil, then that presents some problems in the recycling process. So not all paper that's collected can actually be recycled well. There's some issues, and they unfortunately end up in landfill. And then it's back into the same process again. So it's a really, really good recyclable product. And the more that we do this, the less we can do of this. And that's a good thing because we don't want to damage that too much. And you know, when you sit here in Thailand, you are such a beautiful green country, so you don't actually realize what is happening worldwide in terms of the decimation of our planet. You know that, just as an added statistic, sustainability, and you've heard that word so many times, I understand that. But sustainability, if I asked you the definition of sustainability, which pertains to all materials, including paper, then it's the balance between the use of our natural resources and the replenishment of them. And at the moment, we are and the scale is really imbalanced. We are using way too much of our natural resources. And if we continue on the trajectory that we're on at the moment, and where we are now, we require just short of 2 planet Earths. So already we're decimating our planet. If we continue on that same trajectory, by 2050, we require 3 planet Earths. And you all know there's only 1 planet Earth. This is it. This is the planet. So we have to conserve as much as we can and recycle and recycle and recycle. I cannot emphasize that enough. And the more that I travel across the world and I see what's happening, especially in this space, because this is what we're talking about this afternoon, is paper. And when I see the amount of deforestation in some countries, it's alarming. It's only when you see it with your own eyes does the impact, you feel the impact. So I want to just mention that because we need everyone involved in this thing. Okay, so you saw the previous slide where we're using thermomechanical, but at the same time we can also use chemical. We can use either or both. Now way back, around about the 15th, 16th century, 17th century, we did only mechanical. More recently, we've now brought in chemicals where we are adding soda, sulfite, and sulfate, and then washing it and bleaching it, and that's all energy that we're using. And you know what energy is? That's creating the imbalance on our natural resources. But now, more recently, say in the last 50, 60 years, we combine those two, and we do thermomechanical, which is a lot quicker, a lot easier, a lot cheaper, but we're still using large amounts of energy. Okay, another diagram just showing it from a different perspective in terms of how we get from the trees ultimately to the paper. Okay, now the thing is, what I find generally is everyone knows that paper comes from trees, and the next time they see it is here. But they don't know about all this stuff that's happening in between. So let's just have a look at that for a moment, of all those processes that are happening, especially in this one here and this one over here. Okay. So it varies somewhat from country to country, and the variance comes in how much is being recycled. How much do we have to use virgin material, in other words, from fresh trees, and how much are we coming back from the marketplace and being processed? Remembering, and you'll see it in a moment, remembering that when you're looking at a high-quality board or high-quality paper, Vogue magazine and these sort of magazines, nice, real classy paper, that invariably is virgin material. In other words, fresh material from the trees, not recycled. When we recycle, unfortunately, the more we recycle, the worse the quality of the material becomes. So then you say to me, and I can read the question in your heads, well, if you say that if you recycle, and the more you recycle, the worse the quality, then what's the point? Because I need a quality item. Well, we can overcome that. If one looks at many boxes, and you can walk through this expo and have a look at any place where you see a carton, pick it up and open it up and look inside. And what you'll find in many cases, especially in the cereal market for breakfast cereal, there they'll use recycled board inside. So it's really rubbish board. Sorry to tell you that, but that's how it is. But on the outside, they laminate very high-class board. And that's how you get a nice finish, a nice image to that graphic display that you see on so many cartons. So you get a nice board on the outside, a much lower grade inside, and that's how we overcome the problem. But at least we are using recycled material. Okay. This machine, which stems back from the late 1600s, early 1700s, it's called a Fordrinia. And this machine is exactly the same machine that was used all those years ago, 300-400 years ago. Hasn't changed. They've made it faster, quicker, better, high performance, more efficient, all those things. But the principles are exactly the same. Now, why I show you this is because I can explain how it works. Because if I showed you this, you can't see anything. It's the same machine, all right? So this is a Fordrinia. You can see how long this thing is. From there to here is about 100 meters, plus minus. Can be up to 120, and a short is about 80. But that shows you some idea of the length of it. So, remember those diagrams I had at the start? Those chips of wood and all those sort of things, they go into this process over here, where it gets ground up, they add boiling water, they boil it up, and it looks like a dirty, grey soup. It's a liquid that really looks not so great. And that's what that head box contains. And then what happens is, on this over here, this moving belt, which is the best part of 80 meters, 100 meters, just this section here, that's where everything happens. So this mulch, if you take egg cartons and you make like a paper mulch from it and lots of water and stir it up, and that's what that head box looks like. So this material in this liquid state is what we put down on this conveyor. And this conveyor is a wire mesh. And we lay down this paper, we lay down this paper pulp, 100% water, on this wire mesh. The wire mesh is moving, and as it moves, we suck off as much water as we can. There's also heating boxes, and we heat it up so it spills as much of that moisture as it can. So here we start with 100% moisture, water, and over here we end with about 80% water. Obviously you cannot use the paper yet, it's 20% water. But you've already got rid of 80% of it, just in that process, over that 100 meters. So when it gets here, I now want to go into a drying process where I add more. That's what the head box looks like. I now put it through a series of rollers, many more rollers that are showing on the screen, many more. And I put that wet material through these rollers, and I remove another 10%. At the same time, I also add in starch and resin and clay fillers and all those good things, because when it comes off that Fordrinia, it's very rough. So all the dips, all the valleys in the material, I'll fill those up with these starch and clay fillers. And I'm putting it through this what they call a calandering process. And that creates the smooth paper that all of you use in photocopies and whatever. That's how we get the ultimate result that we're looking at in paper. Now, does anyone know, if I said that paper that you use at home is around about the 8% mark? Why I say about is because depending on the humidity of your country, but around 8%. What would happen if it was only 2% moisture? What would happen to the paper? It would? It'll be brittle, exactly. It'll be brittle and break. Now, some of you have seen that. Maybe you've got a grandmother that has some really old books, and you want to be really careful when you turn the pages because they just sort of crumble. That's because all the moisture has been taken out over time. So the paper that you see around here is all sitting at around 8%. Outside might be around 10%, okay? So we've got to have moisture in paper. We cannot remove all the moisture. It serves a very important part of the paper making process. Okay, let's now, so you've looked at paper, and in paper is also grain direction. But I'm going to come to the grain direction in a moment, because grain direction is very important. When we manufacture a carton, remember I've been talking about paper, and now all of a sudden I'm talking about cartons, but cartons is also a form of paper. All it is, it's thicker paper, not necessarily lamination. We can laminate, yes, and I told you that in a moment ago. But when I go back to the Fordrinia, when I go back to here, if I want to make board, all I do is I make this laying down process thicker. And that's how I get board. So now the question might be, when we talk about paper, we talk grams per square meter. When we talk board, we talk microns. So when does it switch from grams per square meter to microns? And anyone have the answer? Well, you know what? All of you are right, because there's no definitive answer. It's around about 280 grams per square meter we switch. But some countries use it in 300, 310, 290, 280, some even 270, to around about 280 grams per square meter. If you don't remember that, use the figure of 300. It's not going to make any difference. At that point, we switch over and we talk about microns. So when we come to making board, we're now going to talk about microns. But the grain is very important. Now, where does the grain come from? Anyone know where the grain of a paper comes from? Same as you get fibers in trees. Those fibers end up in the paper. And those fibers create the grain. Now, a slow-growing tree produces short fibers. A fast-growing tree produces long fibers. And the long fibers give us good grain direction. Short fibers, not so great. And why is that? Because, remember I told you a little moment ago that when you take recycled paper and you recycle again, you're mulching it every time and you're breaking down the fibers. And as the fibers get shorter and shorter and shorter, so the quality of the board gets worse and worse and worse. Okay, so fibers create the grain, and grain is very important. So why is the grain very important? Let me show you what I'm referring to here. I've given up. Change. This one page? All right, no, what I want is this. I need you in the front. I need you in the front. Okay. I want to show you how important grain direction is. Even this piece of paper has got grain direction. Now, some of you know this, so don't worry too much about that. But first, you just hold that microphone. I want to show you how you can do this at home or in your workspace or whatever it is. If you're involved in paper and board, then you need to at least know one way of checking grain direction. So I'm going to show you one way of checking grain direction. So if you can come and hold this, fine. I want it like that. On both fingers. Same, must be even. You, no. You hold your fingers like that. Don't move your hands. No, don't close. Don't close. Open your fingers. All right, don't close. All right, close. All right. You see how much that's bending? All right. Now you mustn't move your hands. All you're going to do is lift your thumbs. That's all you're going to do. Keep your hands steady. All right. Lift your thumbs. Lift your thumb. Open your thumbs. Yep. Close your thumbs. All right. Do you see any difference there? So that tells you the grain direction. Because where the grain bends more, that means the grain's running like this. Sorry, put it there. That one's bending more, so therefore the grain is running like that. When I do it this way, it's not as much, so therefore the grain is running this way. And thank you very much. So you do the same with board, only it won't bend as much. It bends far more with paper, obviously, right? Another way is you can take a piece of paper, but a small piece, like that size. You can do this at home tonight, and you just wet this. Put it in a little pan of water, wet it nicely, and then put it down and you watch it curl. And when it curls like that, then your grain direction, if it curls like that, like my hand, the grains are running this way, right? Because if the grains are running that way, it's forcing it flat. So this is how we tell grain direction. And for the folk that are making board items like cartons, they have to know the grain direction, because the grain direction is exceptionally important for the cartoning people. So when they make the carton, you put it on a cartoning machine. When the grain direction is in the right direction, that influences or makes it easier for the machine to handle. So you can have faster processing speeds or faster cartoning speeds. So direct correlation. So make sure you are aware of grain direction. Okay. So we're going to look at printing, cutting, creasing, stripping, and folding. So when we manufacture a carton, we have what we call a die, D-I-E. A die is something that cuts it to the size we want. So in this particular case, I'm cutting it to that size, and I'm putting a crease down the middle. That is just to show you very elementary what it looks like. You get very involved and very intricate dies, and you can cut one carton, you can cut 8 cartons, 16 cartons, 32 cartons, 64 cartons, 128, depending on the size of your machine. And then as your carton increases, so your die has to increase as well. So that die is, you're putting the board in and you're bringing a cutting knife that stamps out on the board and cuts the board to the shape you want. And where you want folds, you put creases. In other words, it's not a cutting knife. You haven't cut it. You've just marked it or indented it so that it bends easy when you're trying to form the carton. All right, so once you've created that carton, you've cut it up. It's now in a pile, but there are pieces on the end that you're going to break away, and that's what that guy's doing there. Is what we call stripping. He's moving away the board that is not part of the carton, and that gets recycled. Once you've stripped it, you're now going to glue it, because you've got it in the flat form, and you want a carton that is made up like a toothpaste carton. You've got a glue line running all the length of the carton, and so you want to put glue on there and glue it. And obviously that's a completely another stage of the process, because gluing is extremely important and very finite as to what glue you use for which cartons. Size of the carton, the type of carton, the material construction, all depends on how you glue it. And you can see it going through a gluing machine here, and the machine folds it after it's put the glue down, the glue line, folds it and holds it down for a few seconds as it moves through the machine. And at the end, you end up with a carton. Let's have a look now at some of those cartons. What I've done here is I'm just taking a photograph that was taken in a museum, just to give you a sort of an understanding of way back in the 1600s how they used to make it. Remember I said that you had this slurry or this grey soup? Well, that's the grey slurry. You've got fire underneath here, And he's mixing it and breaking it, mechanically breaking it down with heat. That wire mesh that I explained on the Ford Rainier, that's it over here, he's holding it. So he can only make one sheet at a time, and he lays down the paper mulch, right? And once he's held it down, he brings it to this person over here, and they put it under this press to try and get out most of the water. What happened next was, this is way back in those 400 or 500 years ago. Once it comes out there, this is very moist still, so they often used to make paper on very nice hot days, put that out to dry outside in the sun to try and get most of the moisture away, and that excess, still that last bit of water they need out, they should put it in another press and pressed it out. And that's how they used to make paper. So that principle of making the paper is no different to how we make it today. We just made it faster and made it more efficient. Okay, so remember I said to you that we stamp out the carton with a die, and this becomes the glue flap, and that's where you put the glue, and it gets stuck there on that machine that I was showing you a moment ago. So this is a tube style carton. Probably the most common of all the cartons that you'll see on show here will be tube style. Different shapes, but they'll still be tubes. In this particular case, you're gluing both ends, closing it up. And your toothpaste carton is this one, as an example. But we also get others. It's still a tube. We just call them something different. This is what they call an alternate tuck-in end. Alternate, that's alternate to that end over there. And the reason why we do this is because the next carton, when we have a whole lot up on a machine, the next carton fits in here. You can see how it will fit in there if you have them alternate. If this flap was over here, you would waste so much more board. And that's why they developed this alternate tuck-in ends, as they call it. The French, anyone from France here, they came up with a design, this design of having alternate tuck-in ends as opposed to this being on the same side. Still a tube carton. This, still a tube carton, just a different shape. It's still a tube. Yeah, we've got lock-in ends. So in other words, the bottom of the carton, it's locked. In that design there, you can see how it gets locked. And what happens there is the product won't fall through. So they either lock it by the design or they glue it closed. So next time you get a jar of hand cream in a box, have a look. And you'll see this same design in a box of cream, hand cream. The Matchbox, well, you know, the Matchbox has been around a couple of 100 years. It hasn't changed. Brilliant, ingenious. If it wasn't ingenious, that someone would have found a better way, and they haven't. They're derivatives of a matchbox, but still the matchbox is the matchbox. And that's, again, it's a tube and a slide. And then we get the tray. And this tray is a whole host, from a pizza box to so many others in terms of size and shape. But trays is a unique style of carton. And you know, us consumers, we always want to see what's inside. And so what do? We cut a hole in it so we can see what's inside. And so that's why we have a window carton. All right, so these names here, I've taken the most generic name across the world and put them down there. But I know, because I've spoken to many Thai folk, for those of you in the room that are from Thailand, you have the same board, you just call it by a different name. So these boards are common across the world. You know, you can only make there's only a limit to what you can do with paper from, wood from the trees. But it does show you that the chipboard is 100% recycled. So that's that really low-class board we find in the inside of cereal cartons, for example. And then when you get to the bottom end of over here, this is the really high-class cartons. So the cosmetic industry, perfume market, they would have that bottom one. The really top class, but it's expensive. And gold embossed and that sort of thing. Okay, don't worry too much about trying to remember all that stuff. just bear in mind there are many varieties of board that are available. It depends on how big your back pocket is or how thick your purse in your handbag is. Determines that. All right. Stiffness is directly related to quality of the board. In other words, what type of tree and what about the fibers? Looking at the fiber quality. Remember I said long fibers and short fibers. That gives you stiffness. So why is stiffness so important? Stiffness is important on fast cartoning machines. So those of you who are involved in factories that are using cartoning machines, you need a better board, unfortunately. If you want it to run efficient, you can run low quality board on a cartoner, yes. You just have to run it slower. So your cost per unit climbs. So now you want to balance. You want to bring the cost of unit down in terms of speed, or do you want to increase the price of the board? That decision you would make within your company. And I just left this in there because they're now starting to make bottles out of paper. And then they line them with an impervious layer of like a lacquer. But according to Carlsberg, they reckon it's going to be the packaging of the future. But let's have a look. We'll see there. Okay, any questions on just normal paper? Okay. Okay, now we're going to move to corrugated. And corrugated is paper. The only difference is I'm putting a couple of layers there of paper. This is paper. That is paper. So don't be misled that corrugated is a type of board. We call it corrugated board. It's actually paper. We just laminate and we put glue there to keep it together, the different paper, to create a stiff carton. Now you can see over here, single face, that's the fluting, and that's the liner. Layers of paper. How much? What thickness? It depends on what you're manufacturing, but ballpark, sort of about 80 grams per square meter. Remember, we're talking paper. But I'll show you exactly what those differences are now in a moment. 80 gram or what thickness paper we're using. And then this single face, we use it more in protection of product. We don't actually, you can't really make a box out of that or a carton. If you want to make a carton, we now have to put another layer on. So now we have a liner, we have the fluting, and we have a liner. And we call it single wall. This we now can create a box from, or a carton from it. Or we can go double wall. So now all of a sudden we've got 2 layers. But in fact, we have 5 layers of paper. 1, 2, 3, 4, 5. If I go to a triple wall, 7 layers of paper. So now it's becoming really, really strong. We can go to 4 layers of paper. You can go to whatever you want to go. There's no limitation. When they make pallets, you know, wooden pallets, they can make pallets from corrugated, and the feet of the pallet is sometimes around 18 layers. So there's no limitation. It's depending on the end use of what it is. And then you can change another. You can change and make it a duplex board where the fluting is 2 layers, just the fluting. So you can see the variation. You can have any variation. No, you can't. You can't have any variation. Because if you want your own variation, your own type, you've got to have really big volumes, like really big volumes. Because these corrugated machines are running so fast that if you flick the switch on and you flick it off, just in that time, as fast as I can move that switch, you probably run around 200, 250 cartons through the machine. So you can imagine, if you want your own, you're going to have really big volumes, big quantities, for them to justify them setting the machine just for you. Okay. Now, I know this means nothing to you, but I just want to, for those of you who are in the corrugated business, this is very valuable. because this is how you determine what board you should be using, and if you export into another country, they then know exactly what board you're using as well. And if you manufacture in another country, you can tell them exactly what you're manufacturing, which fluting profile, it's these letters here, you are using. Now there are many more. I'm only giving you a snapshot. All right. The most common ones in the industry is A, C, and B. Now you might say, well, why don't you put B in there? Good question. The problem was, or why that is so, is C was never here. Way back when, it was A and B. And then some smart person came along and said, hang on, we don't want A or B. We want another one. And it was the thickness in between. So instead of renaming them all, they stuck a C in the middle. That's how it happened. Anyway, all right. So listen carefully when I do this. The fluting, remember that's that fluting there. All right. No, wrong way. That's the fluting. So that first column is the height of that flute. The height of the flute, right? This column here is the average number of flutes in 1 meter. So, if I go back here, if I measure 1 meter from there to there, and that's 1 meter, how many flutes are here, right? That is the second column. This one here, you call that factor. If I take this flute and I put it on a table and then I flatten it, it was 1 meter, well, that's 1 meter from there, but when I flatten it, it ends up maybe 1.4 meters, all right? And that's where this one comes from. So when you give this number here, a B flute, to any corrugated manufacturer in the world, they know what you're referring to when it comes to those. They know exactly what you want. So now you all know how to read a B flute board or a C flute board. What I've done here is I'm just showing you the whole lot of them. You can see the variations. You don't have to study those, but at least to give an idea that how many there are around. There are heaps of different boards. Just by varying the thickness of the paper and varying the amount of fluting and how many flutes in a meter. And then you can see what I'm referring to. There's the height, 1.5, 3, 4, and you can see how different it is. And you know from logic, physics, is if you have that is much stronger than that, all right? I think all of you can work that out. So that's what they're saying here. If you can see yourself here, that one over there is going to take way more vertical pressure than this over here. This is going to collapse before that one collapses. So you want to determine what are you packing, how high are you packing it on the pallets, are you going to road freight it, or how are you going to move it from Bangkok up to northern Thailand, all these sort of things. You want to know the geographics of the movement, the supply chain, before you can determine what type of board. And of course the contents, and whether the contents are self-supporting or not. Self-supporting. So those with a can of water is self-supporting. You don't need board to help you. The board is merely there to contain the cans in the carton. If you've got a packet of potato chips, crisps, there you need support from the carton. Otherwise, you'll end up with, instead of nice big pieces of potato chips, they're all crushed. Right, all stands to reason. What I'm showing you here is a corrugated board. How do we design this thing, and what are the measurements that we are dealing with when we're trying to make the box up? Because ultimately, that is the inside of the box, and this is the width of the box. So those are the three dimensions. The other dimension we need to know is, are we dealing with internal dimensions, or are we dealing with external dimensions? So once you've made the box up, external dimensions are very different to the internal dimensions. The thickness of the board you have to allow for when you're designing how many of these boxes fit on a pallet. Now, unfortunately, we have problems in corrugated manufacture. And these are the main problems. Are there any others? Yes, there are. But those are the main ones. So let's just go through those. Warp. You get warp when you use moisture. So here in Thailand, you guys will have lots of those problems. Paper absorbs moisture. Can't get away from that. That's just how it is. And that's what happens when it absorbs moisture. Secondly, delamination. Yeah, you've got adhesive failure. And so the liner is coming loose from the fluting. Softboard. Well, remember I told you that we're dealing with a natural product here. We're dealing with wood. We're dealing with a tree. Some trees have soft fibers, other ones are hard. Short-growing, slow-growing trees and fast-growing trees. So you get soft woods and hardwoods. And we're making it from it, so you're going to end up with soft and hard board. Shy liner is when we are manufacturing in this case, a single face. We've got a liner, fluting, and a liner. So you've got three big jumbo reels feeding the machine that laminates this together. You can clearly know yourself that the size of that amount of paper on every roll, those three rolls, will never be the same. Somewhere, one is going to be shorter than the others, and that's what creates a shy liner. The paper ran out, all right? So you just got to put it one side. But unfortunately, I told you that these machines are running so fast, the human eye can't watch it. So sometimes even the electronics doesn't pick it up, and you end up with this coming to your factory. And you think, well, why didn't they find that when they were manufacturing it? Well, it's not so easy. Not so easy. Washboarding. So this is what washboarding looks like. You can see it's a bit lighter in this area over here of printing. And what happens is when we have excess glue, this is more glue than there, you can see, and so it dips. And when that dips like that, what happens is when you try and print on here, you're on a printing plate, the printing plate can't reach here, or it just touches, all right? It's not a nice firm print, and so you end up with you don't have much ink in that particular area, okay? And that's what we call washboarding. Why do we call it washboarding? Mrs. Pellegrino, do you know why we call it washboarding? You don't. Well, let me explain. If you take a pair of jeans and you drop oil on your jeans, and now you want to try and wash it out. So when you get home, you take your jeans and you've got a mark on it, you put some soap there, and then you start rubbing. But then you rub too much. You know what's going to happen. It's going to go to some light area on your jeans, trying to get the oil out. But that motion creates that lightness. And it's the same as many, many years ago. Folk used to wash their washing down at the riverside, and they had a board running down to the water, and they used to wash their clothes on this board, and that's where the word washboarding comes from. Same word over here that we use. Okay. And then also with excessive glue, other than washboarding, you can also see we get this sort of sagging effect when there's too much glue. So the glue application in the manufacture of board is very important. More important than you think. You think just slap on the glue and make it work. It doesn't work like that, because you've got a very porous material. Paper's porous, so it absorbs water. It absorbs adhesive. And then you've got a substandard result. All right? I'm just throwing out a whole lot of designs because the sky's the limit, depending on your mind, what you can design. And I've seen such great designs, not only in cartons, they make out of corrugated board. I've seen them make elephants. I've seen them make kangaroos. I've seen them make dogs. I've seen them make desks, chairs, tables from corrugated board. So anything can be made from a corrugated paper, corrugated board. You know, again, a whole lot of designs. But the one thing that we really focus on is this one over here. On a stack of cartons, this is the one we keep our eye on, and that's where we do the tests. Because that tells us if we've chosen the right construction. Remember that A, B, C, and all those different boards? That's where you look to see how this thing is performing as to what vertical pressure it can take. Whoopsie. Also, the other thing that you must understand with cartons is that when you put them on the pallets, how are you going to stack them? Because the stacking determines the design, all right? And the design of this carton, you can see here, these are interlocked. You can see how they overlap there. So it's not lined up in one, like this one here. This is column stacking. So you can just imagine yourself, if you're driving a forklift and you want a whole pallet load of this on you and you want to go a little bit faster than you should and you go around the corner, you know what's going to happen here. The whole column's going to fall over. Whereas over here, it's interlocked. So then you were saying to me, well, I don't want the column stacking. I'll go interlocking every time. No, you won't go interlocking every time. Because depending on your weight of the contents, this is a much stronger configuration. Why? Because the corners of a carton is where the strength is. So this gives you a way stronger pallet configuration. So yeah, I can stack it much higher because it's a much stronger design because of the strength in the corners. Whereas though this one is much, much weaker. I cannot stack it as high. So again, you as the packaging person has got to make those sort of decisions. Do you want interlocking or do you want column? So you want it designed accordingly. Or another option is just throw a net around it. Put edges on it. So that's what some people have done if they can't overcome that problem between interlocking and column stacking. All right? I'm not going to go through this. All I want to tell you here is these are all the testing aspects that one can test for in a carton. And then more, there's another page of them. And the reason why we have to do this is because these are tests that help us determine, back to the table, A, B, C, D, this is where we determine it. So we send it off to a laboratory and they test it for us. You don't have to test it. As long as you know there are tests that are available, that's important. And where and who tests them. But the majority of corrugated manufacturers around the world, they do all these tests. Just tell them which ones you want done, because that helps you make your decision. If you want to go a little bit thinner and save money on your board, you do these tests. You determine that figure. All right. And that is it for now, until we start plastics. Are there any questions? None? I don't believe it. Everyone happy with paper and board? No questions? All right. Anyone of you remember this? I'm getting some nods, but not many. Not many. All right, so those of you who did chemistry at school or at university will remember this. This is the periodic table. And when we talk about plastics, we refer to this. But don't be alarmed, don't be scared. If you've never done chemistry in your life, that's fine. We'll keep it easy. We'll keep it easy and simple for all of you that have not done it. I just mention this because there's a lot of polymer chemistry in plastics. Okay, so we're going to go straight into plastics, and all of you know what I'm referring to. So when we come to plastic, but why do we call it sometimes plastics, sometimes polymers? Anyone know the answer? It's a very loose word. Why polymers sometimes? Why plastics another time? Easy way to remember is in the raw material state before we've created any of these products here. we call it polymers. Those are the polymers. When we mold an article and we produce this, that's when we refer to it as a plastic. So it's a plastic container made from polymers, okay? Just so you know the difference. Again, stop me whenever you can. Of all our major materials, metal, paperboard and paper, glass, plastics is the newest one, all right? However, how new is plastics? Plastic been around a long time. The first plastics that was being worked on and with was around about 1890. So it's a long time ago. That's like 130 odd years ago. They already started using plastics, but not for packaging. Not until the Second World War. And what happened in the Second World War, bearing in mind this is oil-based. Plastics comes from oil, comes out in the ground. It then gets refined, and we only use 5% of the total oil production ends up in plastics. And then of those plastics, we only use a fraction of them because the molding industry uses huge amounts of plastic. So we use a very small amount of plastics. And yet we're doing a lot of harm to our environment. Anyway, okay, so what happened was the Second World War was around, and you had the Allied forces, you had the Germans fighting against each other, and the Germans wanted to create a material that could not be picked up by the radar of the Allied forces. And they found that plastics worked. So they then used that as a way of getting around the radar systems of the Allied forces. The good thing is, the war wasn't good, but the good thing was that when the war came to an end, the development of plastics did not come to an end. That is when it took off in the packaging industry. Did you know that, Mrs. Pellegrino? You did, that's good. So that's when we started doing something with plastics that helped us in the packaging arena. So around about 1950, roughly, really broad brush figure, 1950, plastics became something for the packaging industry. And as you can see over here, I was telling you about the 5%. We're only using part of that 5% ends up in our packaging area. Okay, so when we're talking about polymers, we get synthetic polymers, and that's what we're going to talk about this afternoon. We also get natural polymers. Natural polymers. Wool, that's a natural polymer. Silk, a natural polymer. Your hair, a natural polymer. All right? We're not going to talk about those. We're going to talk about synthetic polymers. One's from oil. Those nice colors. All right. The word polymer, poly meaning many. It's a Greek word, polymer. Poly meaning many, mer meaning units. Many units. So where are these units? Yeah, the units are. These are the units that make up a polymer. That's carbon, that's hydrogen. Remember the periodic table I showed you at the start? And you join up these carbons and hydrogens, and all these units, many monomers, each one is a monomer. You join them all up, you get a polymer. Mono, one. Poly, many. So many units. So this one over here is in fact polyethylene. Polyethylene is just carbon and hydrogen, as opposed to the other polymers where we're adding some other elements to it. So we join those all up and we get long chains like this. You can't see it with the human eye. Scanning electron microscope, you might be able to see it. But when we write it out, don't worry too much about this. I'm just telling you so you know where it all works and how it comes about. It's carbon and a hydrogen, and these are all linked long chains, right? And we just write it out as CH2. So CH2 to the N gives you endless, infinity, all right? So how much would make polyethylene? Probably a few thousand, and you get polyethylene as an idea. Okay. I'm explaining to you the difference between polymers and plastics, but this is what once we start creating the polymer from that oil, this is what we end up with. when we deal with these synthetic polymers, we've got two classes. You've got to remember this. The one is a thermoset, and the other is a thermoplastic. I'm going to deal with thermoplastics today, but before I do, I want to explain to you about a thermoset, because many years ago, before probably most of you, maybe those with grey hair will remember, in their time they used to use thermosets in packaging. So a thermoset, once you've molded it, you cannot heat it up to remold. So it sets. The word set means you cannot reheat it. It'll be like that forever. So once you've molded these pot or pan handles, this is urea formaldehyde. Some of you might remember the word Bakelite. This is Bakelite, urea formaldehyde. And that you cannot remelt. It's a thermoset. When I first came into the industry in the mid-80s, we used to use them for closures on pharmaceutical products. We don't use them at all in the industry anymore. All of our stuff is now thermoplastics, and why? Because we want to recycle. Okay, so let's go to thermoplastic, but that's the more exciting part. Well, I think so for that. All right, so now we can reheat these and over and over and over and over. How many times can you reheat and remold? Anyone know? Many times as you like. So that means these figures thrown around, that 7 times is the number. And then last year, a university in Austria proved that it could do it 25 times. Well, you know what? I say, and this is me, not those, how do you know it means recycle 25 times? Because if I take a bottle, any bottle, and I show you the bottle, I say, how many times has this been recycled? You don't know. In fact, no one knows. So how do you know if it's 7 times or 25 times? So I'll leave it there. You can recycle as many times as you like. If you took that same bottle and don't add anything to it, and then go over and over and over, yes, ultimately you'll weaken the molecular structure. Absolutely. But that doesn't happen in industry. We don't cycle one bottle over and over. We put masses, like a few 100,000 in there when we're recycling. So that explains the scenario where you can recycle and carry on recycling. Again, I will tell you when you've got to really listen. You don't really have to listen now. But all I'm showing you is that these lines are those chains I showed you with CH2, 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 forever, all right? Each line there represents that. But what I'm explaining here is when you've got high-density polyethylene, low-density polyethylene, and linear low-density polyethylene, this molecular structure changes. That's why the characteristic or the performance of those 3 different polyethylenes behave differently. This is why they behave differently, okay? Because some are linear, some are branched, some are not so long, but they're still branched, that sort of thing. So just be aware of that. When someone asks you what's the difference between linear low and low density? And then you can very politely explain, well, that all rests in the molecular structure and how it's branched. And they'll think, wow, man, you're clever. How do you know all that? And you tell them, well, you came to the ProPack Asia and you listened to it. That's how you know it. All right, let's deal with some of the different plastics. First one, you all know that at the bottom of a bottle, is there, the gentleman at the back, that bottle in your hand, is there a number underneath it? Is there a triangle? Big mistake, because that bottle should be this one here. It should have a number 1 underneath it. So whoever manufactured that bottle needs to be reprimanded, because they must have a 1 underneath, because then we know what to recycle. Not everyone in this room knows from looking here to there that I can tell that it's a PET bottle. We've got to cater for the masses. The masses don't know that, but they can read 1, 2, 3, 4. So if you put a 1 under there, we know it's PET, and we know where to put it to recycle it. And PET is the clearest plastic that we know closest to glass. So when they created PET way back, they were trying to copy the look of glass. And they got pretty close. If you think about it, I mean, that bottle in that gentleman's hand looks pretty clear. Am I right? It looks pretty good. I mean, if it was like dirty and not so nice and shiny, you'd think twice about drinking the water inside it. But it looks good. It looks upper class. Am I right, Mrs. Pellegrino? Exactly. It looks smart. PET is a great product, and you can see what we are doing with it. The nice thing about this, it's got a very high impact strength. So you can take PET, fill it up with water, and drop it from the roof, this roof here, and it won't break. High impact strength. Okay, when it comes to oxygen transmission rates and water transmission rates, there the different polymers vary, and I'll show you a table about that towards the end of this presentation. The second one, I'm going to put them together, is number 2, and that's polyethylene, high density. Number 4, polyethylene, low density. Remember the branching of the molecular chains? CH2, 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 right, to the N. Okay, so you can see there, again, it's on the branching of the structures that give you that different types of polyethylene. They're still polyethylene, so they're still in the same class. So we can always recycle them. We, in fact, recycle them together if we wanted to. You won't come out with pure linear low afterwards, but you can use them in the recycling. Oh, sorry, let me just note back one. So one of the things about polyethylene, bear this in mind, you can check tonight when you're at home. Polyethylene is one of those products that if you take your nail and you run your nail over the surface of this milk bottle, it's what we call the orange peel effect. You know what an orange is? A fruit? And you know the surface? It's not 100% smooth like an apple. It's got all that little, right? Now that same effect, it's called the orange peel effect. We have it on polyethylene. Very general statement, but at least it'll give you some indication if ever you can't find the number underneath, right? The next one I want to deal with, oopsie, the wrong way, is number 3, polyvinyl chloride. Polyvinyl chloride. This one we used to use a lot in packaging in years gone by. We've slowed in that, and we use less and less these days. There was a big user in the pharmaceutical industry when I first started working. But we've reduced the amount that we use simply because when you are remolding, the gases that are given off are potentially carcinogenic. So we don't want that. And so we're starting to use less of them. In this form like this, there's no problem. It's not going to harm you. It's in the processing, all right? So, but it's well priced. It's good on water vapor and on oxygen barrier. So it's great. Pricing's good. So you think, wow, man, that's great. Why don't we use it for everything? Well, the problem is, as I mentioned, and that's why the pharmaceutical industry used to use it for these bottles in a big way across the world. No more, because of that carcinogenic nature of polyvinyl chloride. Number 5 is polypropylene. How do you tell if it's polypropylene, Alexa? How do you tell if a product is polypropylene? You don't know. Then you listen. I'll explain to you. Whenever you see this, Alexa, whenever you see a closure with a hinge on it, you know it's polypropylene. It's the only plastic known to man that will do this. Are you listening? When you do this over and over, it will not break. You can mold those closures from any other plastic. Yes, you can, but it won't work. Because the first time you start doing this, it'll break. Whereas the polypropylene, you can do it 1,000 times, and it won't break. So that's how you know it's polypropylene. The other aspect or characteristic of polypropylene, it's nice and shiny. It's got a nice smooth surface. And so a lot of closures are using this product. And have a look around at home tonight, have a look at some of the items in the kitchen, and you'll see. And you'll find that in your cleaning products, window cleaning and floor cleaning and toilet cleaning. Those are all polypropylene closures. You won't forget, Alexa, you won't forget polypropylene. Exactly. Exactly. All right. Polystyrene. Now, polystyrene, when we talk expanded polystyrene, that's the white one we see across the countryside, floating down the rivers and in the sea and on the beaches. That's expanded polystyrene. So don't just know that there's a difference. There we're aerating it in the process. But polystyrene, we make a lot of these things, yogurt tubs. The thing about polystyrene, the characteristic of polystyrene, it is very brittle, very brittle. So you can easily, if you squeeze it and it makes that crackling noise as though it wants to break, you know it's polystyrene. It's the only plastic that does that. So each plastic has a bit of a characteristic to it. And that's what makes it easy to try and makes it easier to identify. All right, and then number 7 is everything else. Well, there's a lot of plastics beyond what I've just told you, the last 6. So that's a lot sitting in 0. All right, so there is a body that is working on this, an association that's trying to classify more of those plastics beyond 1 to 6. We can't put everything in 7. Because 7, then they say, well, that can't be recycled. Well, then they can. Many of them can be recycled. This, one of them being polyvinylidene chloride. And don't mix it up with polyvinyl dichloride, 2 different compounds. But this material in pharmaceutical, the majority of pharmaceutical, when you see a blister pack, the clear side is PVDC. High barrier for oxygen, high barrier for water. So then you would say, well, hang on, if that's so good, why don't we use that for everything? So why don't we use it for everything? Why? Why not? Alexa, why don't we use PVDC for everything if it's so good? Not entirely. Henke, do you know? Why don't we use it for everything? Yeah, but it's like PVC, but it's also very expensive. And so the economics, we always have to remember economics in packaging. Always, always, always. We think we've found the solution, and then it affects our back pocket, and it costs us more. So now you want to find another material that is cheaper, but maybe as good. But maybe it's not as good, so maybe it doesn't give us the shelf life. But that's the reality, because if we didn't worry about price, we could put everything in glass. Problem solved. But we know that glass, it's fragile, and it's expensive, and it's heavy. So it doesn't fit, doesn't suit our pocket. So that's why we use plastics. But even in the plastic world, we can't use any plastic. We'd love to use more of this. We'd love to use more nylons, for example. Now, not you, Henke, because I know you know the answer, but is there anyone in this room, because polyamide, an example of polyamide, the ladies will know, Mrs. Pellegrino, is nylon. Where does the word nylon come from? Anyone know where the word nylon comes from? N-Y-L-O-N. Henke, I'm watching you. N-Y-L-O-N. Where does that word come from? You've all heard the word. It's a polyamide. Where's the word come from? No one know? All right, let me tell you, then you're the only people in this area, in this Propac Asia, that know the answer. Nylon, N-Y-L. Now, DuPont are the manufacturers of nylon, which is a polyamide, an example of a polyamide. Many years ago, when they invented nylon, they had a number of laboratories working on it. One of them was in the United States. The other one was in the United Kingdom. And they were on the breakthrough of this invention. And DuPont wanted to recognize both laboratories. Are you listening? They wanted to recognize both. And the answer is nylon is New York, L-O-N, London. Nylon. So they recognize the laboratory in London and they recognize the laboratory in New York. That's where the word came from. So now you know forever. So this is a great product, specific uses in it, nice barrier properties, hence why we use it in sort of packing your food. But it can be pricey as well. Let's look at some of the others, not so much in packaging, but just so you know, when you use safety glasses, for example, that's a polycarbonate, high impact strength. Yep, yeah. CDs for the older generation, you guys remember those. What about ABS? We never refer to the full name, acrylonitrile butadiene styrene, ABS. But some of you will remember, the older generation, yeah, again, the ones with grey hair will remember that dashboards years ago used to crack in the sun. When last did you see a new car or a more recent car with a cracked dashboard? You don't see it anymore because we use ABS, and ABS has got its deference of UV rays is very good. So it's a great product for that. EVOH, now this one is really nice. This is great for water and for oxygen, beautiful for food, but unfortunately it is high priced. So again, economics comes into it when you're trying to consider, because we know it's good. We know it's good, but you can't always use a product where you can't always use a packaging on a product where the product cannot support it in terms of pricing, okay? It's not the cosmetics industry. The cosmetics industry and the pharmaceutical industry is a different ballgame. There, the product can support increased cost of packaging, but not in the food sector. Okay, I'm going to go through reasonably fast just so that you know how do we make. We've told you all these different materials. How do you now manufacture them? Okay, so we've got to have an extruder. No extruder, no manufacturing happening. Must have an extruder. So in the feeder, that's where we put the raw material. They're made of little pellets. Put it in there. Then it goes through this Archimedes screw. Archimedes, chap that invented this. Archimedes, why this is so important is that the Archimedes screw always forces the product to the front as it turns. So a great invention by Mr. Archimedes all those years ago. All right? And as it comes through here, it heats up those pellets and makes it into a soft material that we can mold. Comes through a die. And then when it passes through the die, it ends up in a mold. And that mold consists of a cavity that allows us to be able to shape a bottle or make whatever we're trying to make out of plastic. Okay, so this explains it far better, but in real life, it looks like that. But you can't really explain it. But you've got to have an extruder to form plastics. All right, so down here, we have the extruder, the one I've just shown you, sits over here. Now you can see that it only forms part of the whole process. So when we're blowing film, for example, all the flexible material at Propac Asia was made in this format, majority of it. So you've got your extruder, here's your die. So this looks like that in real life. But I can't explain it there, it's not so easy to explain. Over here I can explain it better. So the polymer comes through the die, and here is air being forced up. This is about 30 meters high, depending on the size of the width of the material you want to make. By the time it reaches there, and is really controlled here in the thickness of it, by the time it reaches there, it's cooled down. Because when it came out here, it was like, excess, depending on what material, but around the 100, 120, 140 mark. By the time it's there, it's cold enough or cool enough to bring together and we wind it up. So, when you're so close, you can't see. All right, so that's the tube, and there are monitors over here watching the thickness of that material, because we don't want it too thick. If we have it too thick, we're wasting money. Remember, it's excess material, and that costs us. If we go too thin, it might not be able to do the job properly. It's too thin for barrier property. Yeah, I won't put you through. You can You can YouTube any of these, they're all on YouTube to show you the actual process. So that was blow and film. When I use extrusion blow molding, now I'm creating a bottle. And when I create the bottle, again, I'm only showing you the molding part because you've seen the extruder now. The extruder is the part that allows the polymer, the paraffin, to come into the mold. And I'm also only showing you one bottle at a time. We seldom mold only one bottle at a time, especially a normal water bottle. We'd probably manufacture 16 or 32 of those at once. But for simplistic sake, so we all understand, I'm showing you a single bottle. That's the paraffin, that's the polymer, the molten polymer that's come out in the extruder. Once it comes in here, the mold closes. I then force air into it and blow it up like a balloon. And then I cool it down. It will be cooled down by various processes, air, but also water through this process here. Cools it down to a temperature that when it falls out, it won't deform when it falls on the ground or it falls into the box. Okay? So that's how we mold, just simple extrusion and then blow molding. Extrusion. Extrusion, and then blow molding. So that's why we call it extrusion blow molding. When we injection blow, in other words, now we injection and then we're blowing. A two-step process. So all those water bottles around here, that the Coke bottle, the PET bottles, they're all made in this process. So what we do is we injection mold this first, and we create a preform, which is a little bottle. You might have seen them around. And that little bottle can immediately be blown, or it can be done tomorrow, or in a month's time, or in another country. We ship it across the world in this form, in this preform size. And that is injection molded. And the reason why we injection, or one of the reasons why we injection molded, is that the closure part, where the closure gets, the thread, it has to be so exact, otherwise it will leak. And I'm sure that all those ladies who have Gucci handbags, one leaking oil bottle in your handbag and you will not be a happy person. So we've got to make sure it's 100% fit of the closure on the thread of the bottle. And we can only ensure that by injection molding. We cannot ensure it if we blow mold. Why? Because when we blow and it cools down, there's contraction. And then it distorts, so it won't fit exactly. So that's why we inject. We inject that first part, and it creates this part exactly every time, and the closure fits on. When we move it to the next phase, as I said, it might be somewhere else, another country, all we do is we're only heating up the body of the bottle. Only the body. That part there remains cold. We only warm up this part, and then we blow it up, like the normal process before. Blow molding. Okay. Stretch blow molding, very similar. The difference here is this is a bigger bottle. It's also a longer bottle, and so there's an amount of stretch that's required. That's the only difference. So the larger those containers, they will undergo stretch blow molding. Okay? Otherwise, the process is similar to the one we've just had. Don't worry about those. Okay, let's come to now just injection. So when we make closures, caps, tops, all those are injection molded. So that red part is the cap. So that's precision. You've got a male die and a female die. Every time those two dies come together, you get 100% correct, accurate molding. But listen carefully, when the orifice of a bottle, in a bottle, when the orifice, which is this over here, the opening, is smaller than the body, we have to blow. You can't injection because the male dye has to come out, as you can see over here. That has to come off again and to pull it apart. So we can't make a bottle where the opening is smaller than the body by injection. Those we have to blow. Injection is a completely different design. But the advantage of injection molding is precision. So precision molding every time. Now what about rotational molding? These are those big water tanks. How do we manufacture them? We have big machines. Now this is a small machine, I understand that. But how do I show you here? This is big, because a water tank can be 1,000 liters or even bigger. So what we do is, that you want to now understand is a big mold. But what we do is, when we rotational mold, it's not blowing mold. We're not blowing, we're not injection. So put that aside completely for those big water tanks. What we do is, we open the mold and we put in the raw pellets that are not molten yet. The raw pellets, we put them in there, and then in each of those three, and then we start omnidirectional, that way, but at the same time it's that way as well. So you can understand now all the different directions, and in that way, and it's heating those pellets, so it's becoming molten as it's moving. It's a much slower process. But by the time that it's now molten, and because of this movement, all that polymer has now coated the inside all over reasonably well. And I use the word reasonably, because when the tank comes out and you cut it in half, you will see that the thickness of the walls varies. There's nothing you can do about that. But we allow for that by adding additional polymer to make sure the thinnest part is, the thinnest section is the minimum. When anything more will be much thicker, but we're putting in more. So it becomes a little bit more expensive because you're adding a bit of excess polymer in it, but it's the only way that we can only way we can mold a large container, like a water tank. Okay. This over here, and this slideshow, it's available for those who want it, no problem at all. But this is a very good thing to have in your drawer next to you on your desk, because it just gives you all the different ones, 1 to 7, 1 to 7, but really 1 to 6 is what we're worrying about. But it gives you a general idea of what's good and what's not that good, depending on what you're packing. So it's a general guide to assess material selection. Now, I just want to do the last two quickly, and that is thermoforming, and the other one I want to do is vacuum forming, all right? So when we make, whoops, what happened there? Okay. Right. When we're making small yogurt tubs, this is the process we use. So you can see you want a male dye, female dye, you've got the foam, you've got this all warmed up, and that comes down, pushes it down, and the air here escapes. Very simplistic. No rocket science. But if it's a very deep, longer container, or we want to speed up the process, then we vacuum it. So now we're sucking it off here. So we can increase the speed. The throughput speed increases, and we can draw it much further down. So this can be much deeper. That's the only difference between vacuum and thermoforming. Okay. Let me go through some flexible, just to give you, remember that very first slide I did in the molding process when we blow the film in that big blowing machine? Okay, that's how we make the film. So those rolls there are the ones that came off the top. And then we slit them to particular widths. But that's the material that we'll use for all these products. and the materials would vary depending on what barrier you require. How do you determine the requirement of the barrier? You have to understand the law of permeation, Fick's law. And if you, those of you who were here yesterday, you would know what Fick's law is. And you have to know Fick's law to determine shelf life. Okay? This just shows you how you can bring different materials together, what we call substrates. Just another word for materials. We can bring it together by various processes, one of them being lamination. And how do we laminate? I'm going to explain that in a moment. So we can bring many different materials together, but you've got to understand the science behind the material before you simply laminate them. Okay. So, as you can see here, I've got various layers that I'm bringing together. Even the glue is a layer, even the print is a layer. When I say it's a layer, it helps in the barrier. How much? Not much, but it's there. You can't deny that it's not there. You can see it, it's there. So you want to take that into account when you're determining the barrier of a lamination. Yeah, I'm joining those layers together. You all know what a Tetra Pak looks like, carton of milk. That's different layers. It's done exactly like this, bringing different layers together by different ways, and those different ways, we'll go through them. Hot melt, extrusion, adhesive, wax, co-extrusion. Let's deal with these quickly. It gives you a nice snapshot of the different types of, Okay, first one, hot melt. I'm sure each and every one of you in the room has somewhere in your life worked with a hot melt glue gun. You have? Well, you know that's the first principle, hot melt lamination. It's exactly the same, only here we do it by an industrial method, by bringing it together over here, the glue, and then cooling it down, and you've joined the two together. No problem. Extrusion laminating, as it comes out the extruder, and all of you know what the extruder looks like, all right? As it comes out the extruder, it's still in the semi-hot molten form, you bring it together. I always say extrusion lamination is like a factory-fitted motor car, things in a motor car that are factory-fitted. That's one of the better ways of lamination, is extrusion lamination. When we apply adhesive, that's like post-factory fitted, because you're bringing it together afterwards and could lead to some trouble. So in the extrusion lamination, you can see over here, they're coming in from the extruders and you're joining the two layers together. Okay, there's the extruder. The next one is adhesive lamination. So it's simple. We're joining it by glue. But we're putting it through an oven to warm it up to activate the glue, and we're bringing in the primary web and the secondary web, the two substrates. Putting glue there, adhesive, and joining it. And then we've got wax lamination. Now, wax lamination is wax. Wax is wax, candle wax. So then you will say to me, but if I warm the wax up, the material will come apart. Now, what's the value of that? No value. No, wrong. Lots of value. Because, think of this, tell me which of you have ever taken a cap off a bottle, like orange juice, and then there's a foil there and you want to pull the foil off? Every time you do that, that is wax lamination. Every time that's wax lamination, because that foil wasn't on the bottle when they made the bottle. In fact, it wasn't on the bottle when they filled the bottle, because they wouldn't be able to fill it. That layer is sitting in the top of the closure, in the cap, and it's being held in the cap by wax lamination. When they put the cap onto the bottle, they pass it through a process called induction sealing. And when it induction seals, number one, that foil attaches itself to the glass bottle or plastic bottle. At the same time, it passes through heat, and the wax melts, and the wax goes into a layer of paper up in that closure, and the foil stays behind. And the foil stays on the bottle, and the paperboard that absorbs the wax stays up in the closure. So when you take the closure off, you see the foil. Have a look next time in the cap, and you'll see there's a paper liner inside the cap. And inside that liner is the wax. So that's wax lamination in action. So it forms a very, very important part. Wax lamination and then co-extrusion. Remember I showed you extrusion? Co-extrusion, 2. You can have more, you can have 4, 6, 7, however many you want. That's the extruders. Now you've got 2 extruders. The other one you only had 1 extruder. And then I'm bringing in the different layers and joining it as it comes out the extruder. So now all of you know the 5 different ways of joining materials together. Simple as that. See, it's not so difficult. It's actually quite easy. This one over here, you've probably seen that word. If you got anything to do with polymers, you would have seen that word or that acronym BOPP. And BOPP is a great invention because it's polypropylene, stands for biaxially orientated polypropylene, but it's polypropylene that all they've done is as it comes out of the extruders, they're actually stretching it in a transverse and a machine direction. So what are they really doing? They're actually just aligning that molecular structure in a really nice way. And that really nice way improves a whole lot of other things. It increases tensile strength, stiffness, moisture, grease barrier, gas barrier. How's that? Same product, and you add all these other features to it. So it's a great invention. And very much the similar price as PP, polypropylene. So fantastic. Now, they've taken it one step further, and they're doing the same to some of the other polymers, which is great. But this is one of the first ones. All right, this one I love. This is metallization. Now, all of you that like some of the chocolate bars, like Crunchy. You like Crunchy? All right, every time you open this on a silver liner, all right, that's metallization. That is not a layer of aluminium foil like you use in the kitchen. No, no, no. This is a different process. This is metallization. Now, how do you understand metallization? Think of a kettle, when you're boiling kettle. So, just sit down a moment. I want to explain this to you because it's very important that you understand metallization because I know you like chocolates. Sit down, please. Sit down, please. And you must understand this. It's very important. I'm nearly finished, nearly finished. So metallization is we take, are you listening? You want to sneak out, just sit down. We take pure aluminium, 99% aluminium, and we heat it up. All right? Remember that? I'll come over here and I say to you, if you boil water against a mirror and the vapor out the spout settles on the mirror and forms droplets, right? Exactly the same happens in metallization, only we do it with aluminium foil in a closed vacuum environment. So we pass the film through, this polymer layer, that material that I showed you earlier, they get blown, and we vaporize the aluminium, and then we cool it, and when it settles, we let it settle on the film. So to the human eye, it looks like it's a layer of foil, but it's not. If you look under a microscope, it's little droplets there. You just can't see the pinholes. So it's not a layer, it's a whole lot of droplets. That's metallization. It looks great. Is it a complete barrier? Not really a complete barrier. Putting a layer of foil is much better, but it services that particular market very well. The market that knows that eat chocolates knows exactly what I'm referring to. And that's metallization. Now you can leave. So, don't forget metallization next time you open a chocolate bar. Think of the water you're boiling on the spout, coming on the mirror. It's the same process, but in a vacuum chamber. In a vacuum chamber. All right. So, all I'm showing you here is you can join up anything you want, as long as you understand the science. Because you don't want to go and join up unnecessarily and over-engineer, because that's economics. Alexa, economics. Always think of economics at any stage when you're designing or thinking about what are you going to laminate or how are you going to laminate. think of the pricing that goes around it. And then I'm giving a whole lot of different examples all the way through. Just to finish off on blister packing, that's the same as thermoforming. Remember we did thermoforming and vacuum forming? That's how we make blisters, exactly the same. Only we do a lot more, making a lot more pockets at one go. The advantage of this particular pack, this one here has got a backing to it, which could be foil, and the other side PVDC. Remember I told you, pharmaceutical we use predominantly PVDC. This one here is PET on PET. Bingo, sustainability, recyclability, and that's the advantage of this one. This came out in 2021. Great invention. It's a huge plus for the pharmaceutical industry. And that's how we do it, so don't worry too much about it. This one here is cold forming. Some of you might have had one of these products. Pharmaceutically, your doctor might have prescribed something that's got foil on foil instead of a clear side. So this is really close to 100% barrier. Why is it not 100%? It's foil, and in an open holes, it won't leak. Why is it not 100%? Because we've joined two layers. So in the middle there, potentially some gases could actually get through. So we can never say it's 100%, all right? So don't bear in mind, but it's still a very good way of creating a very good barrier for certain pharmaceuticals. Okay, that's just an advantage of blister, don't worry too much about it. So when we choose the correct application, these are the things that we must think about. This is what I've covered in the last hour. All these things here. See the last one? Always remember economics when it comes to packaging. Unfortunately, we've got to consider the commercial aspects. Sometimes we don't want to, but we do have to. And that's it. Any questions? None? So I can maybe ask a question then. Mrs. Atlat, you remember metallization. Will you be able to explain metallization? Yeah. No? Okay. All right. But you will always, all of you will remember metallization. I love explaining metallization because when you explain the kettle, then people get the vision in their brain. So it's not a difficult process, but a very effective process. Thank you very much, everyone. Have a good evening.
Thank you. Thank you very much to Professor Pierre Pienaar, the president of WPO, World Packaging Organization. All right, today we have got a lot of useful information about packaging today. Okay, have you fun for the presentation today? Our guest today? Are you? Okay, good, right? Yes, of course. Today's we are honored to welcome and invite all the speakers from WPO's experts to inform everyone and to give us an useful information about the packaging. Thank you so much for our distinguished speakers today. All right, ladies and gentlemen, we all come to for the finally session. That anyone, do you have any question to ask for more information from the speakers? No. Oh, okay. Everyone get it, right? Thank you so much for joining us today. And tomorrow we also have the special and the interesting topics that we invite many speakers, both in Thailand and foreigners, come to have some speech for everyone tomorrow right here. And for tomorrow, we will start the seminar at 10 o'clock until 17 or the 5 p.m. All right, so I would like to invite everyone once again tomorrow, and for the last day is Saturday, so you can come here. All right, to come here and meet our special guests and our honorable guests or the special speakers from many places around the world. Okay, so tomorrow we have the topic of packaging trend daily update by our Professor Pierre. Okay, he is the president of the WPO, and he will come back again tomorrow to see everyone, you all. Okay, in the morning to update for the packaging, daily update. All right, and then after that, the challenge of sustainability, how important for flexible packaging. Okay, the flexor printing and alternative printing technology for Asia. And after that, we talk about how Asahi's water washable plate can be game changer in the flexible packaging market by our speakers. Monkesh Beach, the director sales for Apex Asia Pacific, and Yosuke Chibushi, South Asia Sales and Marketing and Overseas Customer Care Team. Okay, for tomorrow. And then after that, Quality Assurance System for Web Processing Industry by Managing Director BST. And then standardization in flexography printing, the way to simplicity and productivity by printing engineering flexor printing specialization. Okay, so everyone, if you want to come here to listen to the speaker tomorrow, you can come here at 10 o'clock onward. And then after that, okay, at 1 p.m., we have trends, trends and development in smart packaging topic by director, the Active and Intelligent Packaging Industry Association. And after that, at 1:30, innovation in meat and poultry packaging by Packaging Development Division Head, CPF Food and R&D Center Company Limited. He is a Thai speaker tomorrow, and CPF is famous in Thailand as well for as a company. And for the next is the role that packaging plays in minimizing food loss and waste, including best practice award-winning examples by Vice President Sustainability and Safe Food World Packaging Organization. Wow, a lot of program tomorrow, right? And after that, for the last two sessions tomorrow, we have two Thai speakers. About the topic of selection of food packaging and e-commerce packaging tests. So tomorrow we have many interesting topics that we would like to invite you all to come and visit right here at the foyer hall 98. So don't miss this, because every day we have many interesting the topic about the packaging from WPO with collaboration with informal markets right here. So please come here to check it out. All right, now, so we come to for the finally session today. So thank you, every one of you, for coming here and joining us for this seminar together. All right, thank you so much and have a nice day. See you tomorrow at 10 o'clock. All right, thank you. You all, I should remind everyone that we will be seeing you again tomorrow here, innovation stage for day 3. In tomorrow, 16, and the last day is 17th of June at 10 till 17 o'clock. So don't miss it at all you guys. Thank you very much for coming here and join us for this special event together. All right, on behalf of the organizer, I would like to thank you, all of you, for coming to join this seminar. This one is very important for you all, and any informative information will be very good for any business or any organization to listen from our speaker every day right here. Thank you very much for coming here, and see you soon for the next day, tomorrow at 10 o'clock. See you for the interesting and very kind of the topics about packaging. Thank you very much. See you tomorrow. ค่ะขอบคุณทุกท่านมากเลยนะคะก็อย่าลืมค่ะว่าวันพรุ่งนี้เรานะคะจะมีสัมมนาแบบนี้ขึ้นเป็นอีกวันที่ 3 เพราะฉะนั้นถ้าหากนะคะแขกผู้มีเกียรติทุกท่านค่ะที่มาเที่ยวชมงานนะคะใน ProPack เอเชีย 2023 แล้วนะคะวันพรุ่งนี้เรายังมีนะคะโปรแกรมค่ะท็อปิกที่สำคัญแล้วก็ที่น่าสนใจอีกมากมาย ทั้งนะคะสปิเกอร์ชาวไทยแล้วก็สปิเกอร์ชาวต่างชาติด้วยค่ะนะสำหรับหัวข้อในวันพรุ่งนี้นะคะก็ได้แก่ Packaging Trend Daily Update นะคะตามด้วย The Challenge of Sustainability How Important is for Flexible Packaging นะคะเริ่มจาก Flexible Printing and Alternative Printing Technology for Asia to be แล้วก็นะคะในเรื่องของ how Asahi's water washable plate can become changer in the flexible packaging market quality assurance system for web processing industry standardization in flexography printing the way to simplicity and productivityนะคะซึ่งหัวข้อเหล่านี้ค่ะนะคะก็จะถูกพูดโดยสปีกเกอร์ของเราไม่ว่าจะเป็นนะคะProduct Manager Flexo Southeast Asia ค่ะนะคะซึ่งคนแรกที่จะมาก็คือคุณกิติกรนะคะซึ่งเป็นคนไทยนะคะก็จะมาบรรยายค่ะนะคะเป็นภาษาอังกฤษให้กับทุกท่านได้ฟังกันที่นี่ในวันพรุ่งนี้ด้วยต่อมานะคะนั่นก็คือนะคะคุณมองเกชค่ะซึ่งเป็น The Director Sales for Apex Asia Pacific ค่ะนะคะหลังจากนั้นก็จะเป็นคุณโยสุเกะโทบุชินะคะ South Asia Sales and Marketing and Overseas Customer Care Team Asahi นะคะหลังจากนั้นค่ะ Managing Director คุณ Ken Fowler BST นะคะและ Damia นะคะ Printing Engineer Flexo Printing Specializationนะคะก็จะมาอธิบายนะคะให้กับทุกท่านได้ฟังกันนะคะในวันพรุ่งนี้ช่วงเช้าก็เรียนเชิญได้นะคะใครที่อยากจะฟังหัวข้อเหล่านี้พบกันเวลา 10 นาฬิกานั่นเองสำหรับวันนี้ดิฉันขอตัวลาไปก่อนนะคะแล้วเจอกันในวันพรุ่งนี้ขอบคุณค่ะ